So again, thank you all for being here tonight in this makeup class. I will start by discussing some things that pertain to the structure of ionic solids and solids in general. And one of the things that is kind of like common in ionic structures and structure of solid materials in general is that they all have defects. This is kind of like expected because having a completely perfect structure is entropically costly. So definitely introducing some defects will increase the entropy of the system, which is favorable in terms of thermodynamics. So there are different kinds of defects. One, the ones that we call intrinsic defects. And we also have those that we call extrinsic. So, so there are basically three kinds of intrinsic defects. Intrinsic defects are defects in which the stoichiometry of the material or the ionic solid doesn't change at all. And basically what happens is that the atoms change positions. So one of these defects is the defect that I have here. It is called the Schottky defect. Let me write it also here in the close to the board. And in the Schottky defect, what happens is that there's an absence. There's an absence of some of the positions are open. Imagine the three-dimensional structure, and then at some point in this sodium chloride structure, for example, in this case, you have vacant positions. So and of course, if you lose a sodium atom, you necessarily have to lose as well a chloride atom because the material has to maintain electron neutrality. What's going to happen with this is that the stoichiometry of the system is going to remain the same, but now you're going to have holes in the structure. This is one of the defects. Yes?
So if it's like CdCl2, the definition for Schottky defect will be -1 Cd and 2 Cl.
It has to be like that. So you need to maintain electron neutrality. So in the case of cadmium that has a +2 charge, then you necessarily have to lose 2 chloride. Yes. So that is one of the defects, the Schottky defect. The other kind of defect is the one that we call the Frenkel defect. And in the Frenkel defect, what happened is, and let me see if I have one slide here, is basically an atom displacement. What happens is that you have probably the silver cation there that is smaller inside, of course, than the chloride. It's probably occupying an octahedral hole, and then it gets displaced at some place different than that it was occupying. So when that happens, atom displacement, that is a Frenkel defect. Notice that in this case, I am not losing atoms, I'm just repositioning atoms. So they can get to a different place in the structure. And finally, the last defect, and I think I have also a slide here, is what we call the atom exchange. And in this case, atoms just reposition. And this kind of like defect, as you can see here in copper, in the alloy of copper and gold, is very common for alloys, in which this kind of like a flipping or exchange can occur. In the case of these are the three main classes of defects, and as I was telling you, they are abundant in solid structures. Of course, there's something else. They're the defects that we call extrinsic defects. And in the case of the extrinsic defects, these defects are due to impurities. Something that is added to the material, something new that is added to the material, that it is not part of the natural material. For example, a very good example of that are gemstones. Let's take, for example, ruby. Ruby is basically aluminum oxide. So, you know, aluminum oxide can crystallize very easily. Standard aluminum oxide doesn't have much value, but when it has traces of chromium, when aluminum oxide has traces of chromium, then it turns red, a beautiful red color that is characteristic of ruby. Another kind of like gemstone in which the defects come is called sapphire. And in the case of sapphire, it's also based on aluminum oxide. But then you have iron 2 and titanium 4 substituting some of the aluminum. What happens is that if iron and titanium are close enough, then they will present photo-induced electron transfer reaction. So there's an energy gap that you can excite, and that excitation will produce photo-induced electron transfer reaction between the iron and the titanium. And that band is blue. So actually that is what gives sapphire the beautiful blue color. So all these are extrinsic defects because in this case you're adding other things, other external elements to your crystal lattice. Questions? Yes?
For the intrinsic defect, will the big position be occupied by the reactive density?
Well, the electron density will spread into these vacancies, but they are fundamentally empty holes. In the same way that the electron density will spread a little bit inside tetrahedral and octahedral holes, right? But it also happens, like for example, some materials, like for example, even sodium chloride. Sometimes when you heat them up at very, very high temperatures, they turn yellowish. And that yellowish color is due to some electrons that get trapped in these holes. And then these electrons kind of like behave like a particle in the box. So they can be excited as well to different transitions. And then the material turns into this beautiful yellow color. So yeah, that, you know, you can sometimes under very special situations, you can trap even electrons in these holes. Any other questions? All right. So there are other things that I want to discuss. For example, I want to talk about lattices and a little bit about ionic radio. And let me see if I found, this is the slide that I want. So there's three things that basically affect the size of an ion or a cation, right? In this case, talking about cations. So what can affect the ionic radius? There are three things that affect the ionic radius. Tell me one. We have talked about all of them.
Effective nuclear charge.
Effective nuclear charge, but I'm looking that will certainly affect the ionic radius. But I'm thinking about something more of the things that we have been talking about in the last classes that is related to effective nuclear charge. For example, now that you mentioned that, what happened to an ion, a cation, let's say, when you move in the periodic table from left to right? Assuming that all have the same charge, right? If you change the charge, then other things are going to happen. But imagine, for example, what's going to happen if you compare rubidium +1 and silver +1. Which one is smaller? Right. Sorry? Silver is going to be smaller. So, and this is a general trend. When you move from left to right in the periodic table, the ionic radius is going to decrease as well. Right? And you can see it here. There's rubidium right there, and there's silver right there. You can see that silver is smaller. Of course, the coordination number here is a little bit, but here is 6. So rubidium, silver is smaller. And this is a general trend. You move to the right in the periodic table, the ionic radius is going to decrease. What else? What happens if I go down the periodic table in the same group?
It's bigger.
The ionic radius is going to increase, right? And you can see probably here, there's lithium, sodium, potassium. You go down the periodic table, the ionic radii increase, right? And well, since we are already talking about this figure, what else can you see in that figure about the ionic radius? Coordination number. What happened with coordination number?
Radius increases.
Right? As the coordination number increases, the radii or the radius of that ion increases as well. So you can see basically for all of them, as you increase the coordination number, the ionic radius. So those three things are important. So now, I would like to talk a little bit about a concept that we know as the lattice energy, or the lattice enthalpy. Actually, yes, there's an energy associated with a lattice. And the higher that energy is, the more stable the lattice is. So, for example, if I need to heat a lattice to 3,000 degrees to actually decompose it, that lattice will be way more stable than a lattice that I need to heat only to 500 degrees, right? So there's an energy associated with the formation of the lattice and the inverse, which will be the dissociation of the lattice. And that is what we call the lattice enthalpy. So I'm going to actually write the definition. It's the standard That's the basic definition of lattice enthalpy. And basically what it says is the following. If you have a material, an ionic solid, for example, the lattice energy is the lattice enthalpy is the energy basically that you need to that you require to take that material from the solid state to the ions in the gas phase. And I know what you're thinking. You must be thinking, that's very cool. How do I calculate the lattice enthalpy of a solid? That's a really good question. I have a really good answer as well. You need to do, you need to perform something that is called the Born-Haber cycle. You actually have to perform a thermodynamic cycle. So let's say that your product, your lattice, is Mx. So your lattice enthalpy will be the enthalpy that you need to produce Mn plus that will be the lattice enthalpy. Actually, if you build a thermodynamic cycle of known enthalpies, then you will be able, and you know all those values, when you sum all the enthalpies that will get you here plus this, it should be 0. That is true for all thermodynamic cycles. I don't know if you understood that, but I'm gonna explain it better. For example, you want to get, so this is the lattice enthalpy. Actually, if we want to make a thermodynamic cycle that gets here, probably we don't want to go that way, although we could. We actually want to go this way. So we're gonna put here the negative of the lattice enthalpy. That's basically if we switch that arrow. So if I want any material, if I want to get the individual materials forming, the individual elements forming a material, basically what I will use, a constant that I can find in books, is what we call the formation enthalpy. Do you remember the formation enthalpy from your general chemistry? What is the formation enthalpy? The enthalpy of formation. Right. It's the energy that gets released when the elements in their natural forms combine to form a material or a substance in general, right? So will be the energy, and I'm assuming that this is a metal, that N is a metal, so it will produce solid plus X. And if I assume that X is a halogen, then it will be X2. And if it's fluorine, it will be a gas. If it's chlorine, it will be a gas too. If it's bromine, it will be a liquid. And if it's iodine, it will be a solid. So I'm going to choose that it's a gas, so it's either fluorine or chlorine, just to make it easier. But it doesn't have to. And then, remember, now I have them separated, so that's good. The only thing is that I need to move in that way because I need to reach here. So actually, what I need to do is to flip this arrow, is to have the negative. So I can go in that way. that I need to do is to apply different enthalpies to this equation or to this diagram to transform M solid into M gas in the ionized state and X2 in the gas phase to X minus in the gas phase. I need to apply different energy. So, for example, what energy, how do you call the energy that is necessary to take a solid directly to the gas phase? If I want to do this process, N gas. How do you call that energy? Sublimation enthalpy, right? So actually I'm going to make this arrow a little bit shorter so I get enough space. Sublimation, right? What else do I need to do with that M? I need to convert it to the cationic form. So how do I do that? Right, since this is just assuming that this X is just -1, so then the charge of the M must be +1, so that's the way that it's here. So we're going to use the first ionization energy. And now our M is in the gas phase and is ionized. And the only problem that we have is that our X2 is in the dimetic form. So what do I need to do there? How do I break that form? Well, we call it dissociation energy, right? That's dissociation enthalpy. So we're going to break that bond. And we're going to form, actually, I have been calling this X2, but the energy of formation will be actually 1/2 of this. So 1/2 of this, 1/2 of this, and then I will only have one X in the gas. Okay, so there's only one thing that we need to do to reach here. What it is? Well, the electron affinity is basically the negative of another quantity, which is the electron gain enthalpy. So what we're actually going to use is the negative of the electron affinity. And that amount is always, or not always, but most of the times negative. So then the arrow is going to be down. Electron gain enthalpy. And that is going to transform my X into X minus. If you notice, we have completed the thermodynamic cycle. We have accounted for every single thing, and now, if I sum all these enthalpies, the sum will be 0. So if I know the values of all these, did I forget to put here the H? Gas. And this is delta H, this dissociation. If I know the values of all those enthalpies, the only value that I don't know is this one, and the sum of all of them is 0, then I can find the value of my lattice. Right? Alright, so, yes?
And exact questions of like the minus signs you use?
It's to invert the arrow. Because, for example, in order for the cycle to be 0, the arrows need to be pointing in this direction, right? But the delta H of formation is actually like this. So in order to have the arrow pointing in the right direction, I need to put a negative sign there.
And then what do you have at the top right under M gas plus X? Right under there, like what do you have at the arrow?
At the arrow?
Yeah.
Enthalpy of dissociation. To break this bond into this X2, to break it into X.
Okay.
And then this arrow, I also need to invert it because the definition of lattice enthalpy is like this. So to make the arrows pointing in the right direction, I need to extend. Right? I can do an example, if you don't mind. Or if you understand it well, then we can move on. What do you prefer, example or we keep going? Example? I knew you would say that. A simple solid, magnesium bromide. It formed beautiful, transparent crystals. Magnesium bromide. The dissociation enthalpy, it will be, or it will require, to dissociate the lattice into magnesium 2 plus 2 bromide ions, all in the gas. Right? You already know that we're going to make the cycle, so the first thing I'm going to do is that I'm going to invert that arrow so I don't forget later. And then the first step of all this reaction is to separate the magnesium and the bromide, or the bromide. So how do we do that? What is the first energy that we're going to put there in our diagram? The enthalpy of formation, right? So we're going to start with that. What is the natural form of magnesium? Solid. What is the natural form of bromine? Liquid. So basically, our enthalpy of formation actually, I need to invert it. I'm going to just give you the value. The enthalpy of formation for magnesium bromide from magnesium solid and bromide liquid is negative 524, but since we inverted, kilojoules per mole. I'm just not gonna put the kilojoules per mole to avoid writing kilojoules per mole 100 times. But so that you know, everything, all these values are kilojoules per mole. So, okay. So what do we need to do now? We can do a lot of things. So what do you prefer to do? We need to get here. So what? Sublimation, right? So sublimation will take magnesium from the solid state to the vapor phase. I'm gonna start writing these arrows small because then I will run out of space there. So this is magnesium in the gas phase, and bromine is still as a liquid here, and the enthalpy is the sublimation enthalpy, and for magnesium is 148 kilojoules per mole. So what is the next step? We can convert the bromine to the gas phase, right? So that is what we call vaporization energy. And for bromine, that is not that difficult. That is just 31 kilojoules per mole. And it will take now everything is in the gas phase. So what is the next step? We can go to dissociation. I'm sorry, this is weird too. So dissociation energy will transform the diagram into two bromine atoms, and that energy is actually 193 kilojoules per mole, the dissociation energy of the vaporization, evaporation, we are talking about it. Vaporization enthalpy evaporation. Yes.
What's the delta energy actually called?
The lattice enthalpy? Yeah, delta H lattice enthalpy. Alright, so what is missing from here? Two steps actually, right? Ionization energy, and here, yes, we need to ionize magnesium twice, right? The +1 and +2 state. So when you look into the tables, in this case, in which it was just one charge, you just get the first ionization energy, but if you have to do it twice, then you have to sum the first and the second ionization energy, right? And we do that, and I already have it here, is 2187 kilojoules per mole. And that is going to give you, I'm going to make a little stair here. That's going to give you magnesium plus 2 bromine atoms. And now, to convert those 2 bromine atoms into 2 bromide atoms, we need what? The negative of the what? Of electron affinity with the electron gain enthalpy. The negative of the electron affinity is the electron gain enthalpy. So basically, for 1 bromine to go to bromide is 331 kilojoules per mole. But since we got 2, then we get twice that. And this energy is and that is basically our cycle. So now, and I'm gonna erase here. Which is 331 times 2 is equal to 0. You can pass this to the other side of the equation, positive sign, sum all these, and basically
Sorry, the 2187, what does that represent?
the 2187. That is the ionization energy for taking magnesium gas and ionize it to, and I'm sorry here, I messed up, to the 2+ state. Questions? Yes.
What is the 193? Is that dissociation?
The 193 is the dissociation energy to take bromine to bromine. Dissociation. Questions? This side, you get 2 extra questions. because this side has used all the questions. All right, is that understood? Because you can calculate, this is the experimental way of calculating lattice enthalpy. There is a formula that you can use as well to calculate lattice enthalpy. You can use what we call, this is what we call the Born-Haber cycle, and you can calculate lattice enthalpy by using what we call the Born-Haber equation. And if I didn't write it before, this is what we call the Born-Haber cycle. So the Born-Haber equation basically says that the lattice enthalpy is proportional to that, which is basically the electrostatic parameter that we have been talking about for a long time. And basically, the lattice enthalpy is going to be high if the product of the charges is high, which means that if I have, for example, cations that are +2 or +3, and anions that are -2 or -3, the ionic bond between those highly charged things is going to be very high, so the lattice enthalpy is going to be high. Also, if the distance between the cation and the anion is small, it means that the interaction between them, the ionic bond between them, is extremely high. So that actually makes sense that the lattice enthalpy is inversely proportional with the distance. But okay, the full equation is this. The lattice energy is equal to the actual value of the product of the charges of the cation and the anion multiplied by the Avogadro's number multiplied by E. It's kind of like, I'm just going to make it cleaner. Don't worry, I'm not going to write everything else. And that is certainly 4 pi So let's start from here. This is Avogadro's number. Zn and Zb are just the charges of the anion and the cation. E squared is the charge of the electron, which is equal, well, it can be equal to different things, but just to give you a number, 1.602 times 10 to the minus 11 coulombs. Zero is the permittivity, which is 8.854 times 10 to the minus 12 inverse joules coulomb square meters to the minus. D is the distance between the cation and the anion, so you can say that D is equal to the ionic radius of A, the ionic radius of B. And you can get that from tables very easily. D star is a constant, which is equal to 34 0.5 picometer. This D and this D are the same quantity, but notice that here, to cancel units with D star, this D needs to be in picometers, but here, to cancel units with the permittivity, this D needs to be in meters. So it is the same value with different units, so don't mess up in the exam, all right? Or in the homework. I'm not saying, just saying. And there's one more thing, and it is this A here. And this A is what we call the Madelung constant. The Madelung constant. And the Madelung constant is dependent on the crystalline structure of the material. If you have a solid cesium chloride structure, the Madelung constant is going to be different than for the sphalerite structure. And let me find that there it is. These are the Madelung constants. So depending of the structure of your solid, then is the Madelung constant that you are going to use. The problem with the Born-Haber equation is that you have to have a previous knowledge of what is the crystalline structure of your solid. If you don't have a previous knowledge, then you cannot choose the right Madelung constant for it. The Born-Haber equation will calculate perfectly or mostly perfectly, will be a good fit to the Born-Haber cycle, so the theoretical value will be a good match with the experimental value. Only is the contribution of the bonding in the lattice is purely ionic. The Born-Haber equation only considers ionic contribution. So when the Born-Haber equation is going to start deviating from the real value? Well, that's going to happen when there is significant covalent contribution between the cations. So let's say, for example, that you have strongly polarizing cations in your lattice. Those lattices will tend to have or to present some covalent contribution. When that happens, the Born-Haber equation will not be able to account for that covalent contribution. It can only account for ionic contribution. So deviations to the Born-Haber equation generally come from covalent contributions that is not being accounted in the formula. But I was telling you that one of the problems with the Born-Haber equation is that you have to have a previous knowledge of what is the structure of the solid. So there's another equation that you can use that you don't need any kind of knowledge about the crystalline structure.
Can I ask a question?
Yes.
So you give the constant for E squared, right?
Oh no, that is for E.
Okay.
Thank you. This is 10 to the minus 11. I could be wrong, but if you have the book and can check it out, 10 to the minus 9. Oh, yes. I have a very bad line. Thank you. Thank you for that. Anyway, for the exam, you don't need to memorize any of these constants. This will be in the exam. If I put 11 in the exam, you will 11. I will assume the consequences.
And for the unit of E0, will that be
That will be C squared.
So
C squared up here, C squared down here, they will cancel each other. Any other questions? All right, so there's another equation that you could use that is called the Kaputinsky equation. And the Kaputinsky equation is similar to the Born-Haber equation, but instead well, this is the Kaputinsky constant, which is equal to 1.21 times 10 to the 5 kilojoules picometer per and N is the number of ions per formula. So that is the Kaputinsky equation is not as precise, it's not as good as the Born-Haber equation. But the good thing about the Kaputinsky equation is that it doesn't require any previous knowledge about the structure of my lattice. So it just uses a standard constant here, which is the Kaputinsky constant. This equation, the Kaputinsky equation, allows you to do things that the Born-Haber equation doesn't, and is the calculation of thermodynamic radius, thermodynamic radii. For example, let's say that I have a lattice, and I can calculate the lattice enthalpy using the Born-Haber cycle, and I put it here, and I know all these parameters. Then the only thing that I don't know that will be a variable will be the distance between the two ions. And then that will allow me to calculate what we call thermodynamic radii. So these things are really not spherical. As you can see, the OH ion, the carbonate ion, these things are not really spherical. But using this equation, we can calculate back what is the distance between two ions, and if we decide, probably randomly, the value of one of them, which most people have decided that O2 to minus is 180, then you can calculate back the radius of any of the other combinations. So basically, this equation will allow you to calculate thermodynamic radii of different things, which is kind of very cool. Yes?
Does this equation only capture ionic contribution as well?
Yes. No covalent contribution whatsoever. And it will suffer from the same limitations that the Born-Haber equation. Questions? All right. If there's no further question, then I would like to talk a little bit about conductivity. Conductivity or metals, semi-metal, semiconductors, all that kind of stuff. let me ask you a question. What is an electricity conductor? Don't tell me that it's a substance that conducts electricity. Although that's true, a conductor is a substance that conducts electricity. But a semiconductor is also a substance that conducts electricity, right? Maybe not as good as a conductor, but it does conduct electricity. So what is the difference between a semiconductor and a conductor? Do you know?
The distance between the field electron band and the unfield.
Well, that's true. That's a little bit more complicated than what I wanted. A more basic. Or what would be the consequence of that? Sorry? Well, the electrons can flow more easily in the metal. That's true. Or in the conductor. But this is the thing. Well, I'm gonna ask you a question. What happens when what happens with the conductivity of a conductor when you increase the temperature? It decreases. Why? So basically, the atoms. Remember what we talked about metals? Metals basically donate electrons to a common sea of electrons, and those electrons need to flow in order to present conductivity. When you increase the temperature, these atoms start vibrating, creating kind of like defects. So the electrons cannot move as easily in between the atoms. So that creates resistance, that decreases the conductivity. So we're going to say that a conductor is a substance in which the conductivity decreases with temperature. All right. What can we say about a semiconductor? That's right. We can say also that it conducts less electricity, in general, less electricity than a conductor, but the main characteristic that identifies a semiconductor is that the conductivity increases. And compare with an insulator. What is an insulator? The conductivity is always low with an insulator. Basically, it doesn't conduct electricity. But if you can measure the conductivity of an insulator, what will happen with temperature? The conductivity will increase or decrease? It will increase as well. But in general terms, an insulator is a material that has very low conductivity. And that conductivity also increases. With time. Also, there's another thing that is called a superconductor. there's no resistance to the flow of electrons in a superconductor as long as it is below the critical temperature. So superconductors need to be very, very cold in order to display superconductivity. If they are above the critical temperature, they will not be superconductors. So let me write that. So, by the way, do you know the joke about the superconductor that goes into a bar? So a superconductor goes into a bar, and the bartender says, we don't serve superconductors here, and the superconductor left without putting any resistance. Come on, it was a good joke. What's the word? The superconductors have zero resistance, zero electrical resistance. When below the critical. Have zero electrical resistance when below the critical temperature. All right? So this is what happens. I think that we talked a little bit about this, but when metals, let's say metals that are conductors, but basically this applies to any solid, start coming together, then these orbitals that get formed, so when you bring two atoms together, when you mix two atomic orbitals, how many molecular orbitals will you form? The sum, if you mix two atomic orbitals, you will get two molecular orbitals. If you sum three atomic orbitals, you will form three molecular orbitals. But if you have a solid in which you can consider putting 1,000 atoms contributing each one atomic orbitals, how many molecular orbitals do you have? 1,000. If you have 1,000,000, how many molecular orbitals you have? 1,000,000. So imagine a material with millions and millions of atoms. When you start forming molecular orbitals, they are not discrete molecular orbitals anymore. They are so close together that now we consider them as a band. They're still molecular orbitals. They are still formed due to the overlap of orbitals that have the same symmetry. But now they are so close together that electrons can basically move between these orbitals very easily. These molecular orbitals. So you can form band structures. If the band is formed from the overlap of s orbitals, it is called an s-band. If the orbitals, if the band is formed from orbitals that are p in character, from p orbitals, it is called a p-band. And if the band is formed from d orbitals, how it is called? Yes, a d-band. So that is the way it is. So we can have different bands, right? So this is what happens. Conductors. Let me see if I have here a better slide. This kind of like exemplify what I was telling you. If you start putting more and more and more orbitals, then you end up forming kind of like a continuum of orbitals that is called a band. But this is what I want to show you. A substance that is a conductor have filled bands. If you have a band completely filled, that material will be an insulator. The electrons cannot freely move in between the orbitals. They are stuck in those positions. So then the material cannot conduct electricity. If the band, I'm talking about here an S band, but it doesn't necessarily have to be an S band. If a band is half full, then the electrons in this band are mobile. They can jump from one molecular orbital to the other and find their way through the solid. Conductors actually have filled bands. The distance between an S band and a P band, but I would say more clearly, the distance between two bands is called a band gap. And you probably have heard that term before, band gap. And basically, it will say something about the conductivity of the material. If this band is the band gap is really small, then if you heat up the material, if you apply some temperature, then you will be able to promote electrons that are in the S band or in the lower band to the upper band, creating holes here and also creating electrons here that will be able to move through this band because it's mostly empty, and holes here that will allow other electrons to occupy those orbitals and move throughout the material. So materials that have full bands that are supposed to be insulators, but the other band is close enough that the electrons can be thermally populated into the other band, are called semiconductors. That is why semiconductors, the conductivity increases with increasing the temperature, because the higher the temperature, the more electrons you can promote into the other band, and then the higher the conductivity. Does that make sense? Well, yes, it does. It's the way it is. So there are two different kinds of semiconductors. It's the same as two different kinds of defects, two different kinds of semiconductors. There are the intrinsic semiconductors. And there are the extrinsic semiconductors. But the intrinsic semiconductors are the ones that have a very small band gap that would be able to promote electrons from the lower band to the upper. And examples of these is, for example, silicon that have a band gap of 1.11 electron volts, or germanium is another semiconductor, have a band gap of 0.66 electron volts. Just to give you an example, carbon, such as diamond, is an insulator and have a band gap of 5.47. So that distance is too large to promote electrons to the conductive band, so the material is basically insulated. So in intrinsic semiconductors, the band gap is small, which allow the promotion of electrons to the upper band. Another definition: this band that is completely full is called the valence band, and this band that is empty is called the conduction band. So you basically promote electrons from the valence band to the conduction. Of course, can have what we call extrinsic semiconductor. And extrinsic semiconductors is when you dope your material with some other element that either have more electrons or less electrons than you. So for example, the extrinsic common type of extrinsic semiconductor is the N-type semiconductor. And the N-type semiconductor, for example, let's take, for example, silicon. There. I can dope silicon with arsenic to form an N-type semiconductor. You can see that silicon is a P2 material. I mean, it has 2 electrons in the p orbital. Arsenic has 3. And the doping is a very delicate process. Actually, the doping species need to be in traces amount. Basically, 1 atom in 10 to the 9, 1 atom of the dopant species. In 10 to the 9 atoms of the material, like for example silicon. But when you have that kind of like proportion, what you form is an N-type semiconductor in which you will form a small band full of electrons close by to the p band. And since this small band that is due to the doping with arsenic is close to the conduction band, then it is easy to promote electrons to that band, and then again the electrons will become mobile, and you will have conductivity. Yes.
Why does one more electron give the donor band?
Sorry?
Or why does having one less electron AS give the donor band?
No, one more.
So AS has one more electron.
AS has one more electron.
So why does that become a donor band at that position?
Well, it's due to the energy. Basically, you don't. It only doesn't. It's not only related to silicon and arsenic. It can only work with any of the elements in the periodic table. For example, you can go to any with arsenic as well, or with Sp. It depends of the kind of semiconductor that you want to make. But when you use an atom that intrinsically has more electrons, the net effect is the creation of a band at a higher energy. The position of that band cannot be exactly predicted. We know what are the positions because we have measured many of these things. And sometimes these bands even fall within the p band. And sometimes the distance to the p band. So whether exactly it's going to fall, we don't know. But what we know for sure is that this band is going to be higher in energy than the S band. And because it's higher in energy, it's going to be closer to the p band. That is for an N-type semiconductor. Let me write here that that's for N-type semiconductors. For the P-type semiconductor, then you're going to do the opposite. For the P-type semiconductor, basically, you're going to dope your material. Let's take, for example, silicon. You're going to dope it with something that has less electrons, like, for example, gallium. If you do that, then what you will do is that you will form a small band there. It's going to be, again, superior in energy to the valence band. But now this band is going to be empty. It's going to be empty because it has one less electron. So now you have an empty band next to the valence band, and then it is easy to promote electrons into that empty band. Again, you will promote electrons here. These electrons are mobile, and you will produce holes here that can be occupied by the other electrons in the band, making the material mobile. So P-type semiconductor, N-type. Questions? This is relatively straightforward, right? So that is basically all that I want you to know about chapter 3. So with that, we finish chapter 3, and tomorrow we're going to start with symmetry and group theory. And I'm going to show you how to make molecular orbitals of clear and quantum. So see you tomorrow.